So welcome everybody to today's talk. We have Ayo from our college talking about combinatorial interpretation of Goncarov polynomials over the lattice of permutations. All yours.
Partitions. Well, yeah, sure. Thank you, Laura. Thank you for the invitation, and thank you everyone for coming to this talk. I know it's been a stressful week for many people, but I mean, you're here anyway, so let's talk about some combinatorics. Okay, so I'll give a brief overview, and hopefully I'll try to stop somewhere in the middle so we can take a break and then we'll come back and finish up. Again, you don't have to understand all of the things on this page. We'll come back to it at the very end, but I just wanted to kind of give an overview of what's happening. So my work is in combinatorics, and I worked under Catherine Yan for my PhD at Texas A&M. And I mean, a lot of her work is in packing functions. So I do a lot of packing functions type of stuff. But so this talk is mostly from the work from my PhD thesis, where I worked on this interesting thing. So I'll kind of just give an overview. So you have some things called basic polynomials, I'll explain, and there's a connection with delta operators. Okay, and then on the other hand, these basic polynomials, of course, are counting some kind of structures. And at the bottom, which you see in green, we have Goncarov polynomials, okay, which are these nice polynomials that come from numerical interpolation theory. Okay, and then it turns out they are connected to these basic polynomials, connected to the structures, connected to delta operators. And I'll explain all of this, and particularly where our own work and contribution was. Okay. So let me go ahead and get started and talk about polynomials of binomial type. So a polynomial sequence is said to be of binomial type if it satisfies expression 1 here. So, I mean, immediately you begin to think of the binomial theorem, right? Because this looks like the binomial theorem, except this is just saying the polynomial when you evaluate at x plus y is equal to n choose k times the kth polynomial evaluated at x times the n minus kth polynomial evaluated at y. And that's true, you know, this is a generalization of the binomial theorem. So you can always think of that as your like go-to example, the power polynomials. So that's the first example. Another example are the lower factorials, okay? So the expression 1, in this case, for the lower factorials, is the well-known Vandermonde identity. Okay, so there are several examples. I'll still list a few examples later on, but for now, I'll just focus on this one. And please feel free to stop me at any point if you have any questions. Okay, so let's move and talk about delta operators. So delta operators are going to be very important for what we're talking about. But before that, throughout the rest of the talk, whenever, you know, we're assuming we're working over a field of characteristic 0 and k, the vector space over k, okay? And so what's a shift operator? A shift operator is just a linear operator from the vector space into itself, where you are shifting things by this factor of a. Okay, so the shift operator E of a. And so here comes the definition of a delta operator. Delta operator is a linear operator from the vector space to itself that commutes with the shift operator. So it's we say it's shift invariant, and for all a in the vector in the field. And also when you act this delta operator on x, you get a non-zero constant. Okay, so any linear operator that behaves this way is called a delta operator. Okay, so what's the connection between binomial type polynomials or polynomials of binomial type and delta operators? It turns out that you can say that a polynomial sequence is called the sequence of basic polynomials of your delta operator if these three conditions are satisfied. One is that your delta operator is degree reducing. Okay, for any of those polynomials, if you pick the polynomial of nth so of course we're assuming each the nth polynomial has degree n. So if you act the delta operator on the nth polynomial, you reduce the degree and multiply, of course, by n. So immediately maybe you're thinking about the differential operator. And that's true because that's like our go-to example. So the second condition is that p sub 0 of x is 1 for all x. And p sub n of 0 is 0. In other words, the constant term is 0 for all of these polynomials. Okay, so if you have this being satisfied, we say that this polynomial sequence is a sequence of basic polynomials for delta. And so the theorem from Moulin and Rota actually says that there is a one-to-one correspondence between delta operators and polynomials of binomial type. So for every delta operator, there's a unique sequence of basic polynomials. So it's the same thing if you hear me say basic polynomials or polynomials of binomial type. It's essentially, there's the same because really every polynomial of binomial type is a basic polynomial for some delta operator. Okay.
So for example, for the following factorial, what is the delta?
Yeah, so I'll give examples just right away. Here it is. So yeah, so like I said, the standard power polynomials, the one, is the differential operator. The following factorials or the lower factorials is E1 minus I, where I is the identity operator. And you can check out these things and see, that you get, it satisfies that expression that it's degree reducing. For the rising factorial, it's I minus E to negative, minus 1. And the Bell polynomials is this polynomials where you have S sub nk, where S sub nk is the Stirling number of second kind. So these polynomials, this is the delta operator that corresponds to that. And for the Abel polynomials, this is the delta operator that corresponds to that. So these are some of the well-known ones. Again, it's not always easy, and I'll talk about that, to be able to get, your delta operators, but there are some that are well-known. So these are just some examples.
And these delta operators are unique to each.
So, sorry, can you say that again?
These delta operators are unique to each basic polynomial.
I'm sorry, I didn't hear you very well. It seems a little low.
Sorry. Okay, can you hear me now?
Okay, yes.
Sorry, I think it's my. Okay, can you hear me now?
Yes.
Is the delta operator unique to each of the basic polynomials?
Yes, exactly. Yeah, that's the whole this Moulin and Rota's theorem tells us that every delta operator has a unique sequence, and conversely, the same thing is true. Yeah. So this is exactly they're unique. Yes. Okay. So let's move forward and talk about how do you characterize this using generating functions. So if you have a basic sequence for delta, okay, so first let's define what is the D indicator. So one of the results of, from Moulin and Ruta's work is that each of your delta operators is actually a formal power series in D. That is, so like I said, D is the differential operator. So you can write a delta operator as a formal power series in D. So whatever formal power series, so if Q of T is the formal power series that satisfies, delta, that is delta is Q of D, then we'll call Q the D indicator for that delta. Okay, so the exponential generating function, we can actually characterize it, and it gives us this function for any polynomial of binomial type. You have exponential x times Q inverse of T. So the compositional inverse times x, that's exponential to the of that is what the exponential generating function is. And so what we say is that your polynomial sequence is the conjugate sequence of lambda, where lambda is the delta operator given by the compositional inverse. And of course, you may say, what happens for the original Q? Well, we say that the sequence is the associated sequence. So associated for the one for which it is the delta in the indicator, and we say it's the conjugate sequence for the compositional inverse. Okay, so this is another way actually to define polynomial sequences of binomial type. So it's equivalent. But the key thing I want to say here is that to be able to go from a polynomial sequence of binomial type to the delta operator, you have to kind of go via this generating function and then find the compositional inverse and then, you know, replace your T with D, and that's your delta operator, okay, in terms of the formal passes. But we know that it's not always easy or straightforward to find the compositional inverse. So that might be a little issue. Okay, but let me leave that for now and then move and talk about the next thing, this interpolation thing. So yes, I mean, this, like I said, you have this problem coming from numerical interpolation theory called Goncarov interpolation. So like I said, just forget about delta for a minute and just think about the differentiation operator. So you take the I derivative and of some polynomial and plug in a value, okay, and then get some other value. That's some kind of special kind of Hamite interpolation. So in this specific case, replace the D operator with delta, okay, just in general. So this one was defined by Lawrence Tringali and my advisor, Yan. They kind of generalized this concept of the Goncarov interpolation problem. And essentially what you're saying is you have two sequences, Z1, Z naught Z1, and so on, B naught B1, and so on up until Bn. And then you have the delta operator. And the question is, we want to find a polynomial of degree n such that when you take the ith delta iterate of this polynomial and evaluate, so E sub Zi is just evaluation. So you evaluate at the point Z sub I, what you get spits out for us B sub I, the corresponding term in the other sequence. So it turns out that when your B sub I is specified to be n factorial times Kronecker delta n comma I, there's a unique solution. And that unique solution is called the generalized Goncarov polynomial. So we'll throw out for the rest of the stock, whenever you see T sub n, this is denoting the generalized Goncarov polynomial. Okay, so let me give just a few examples of what this looks like. So for two of those cases I mentioned earlier, when your delta is your differentiation operator, then remember that the corresponding polynomial binomial type is the power sequence. Okay, so essentially what's happening whenever your Z naught, in the case where your Z's are just, it's a constant sequence. Okay, Z naught is Z1 is Z, all of that is A. Then it turns out your Goncarov polynomial is just a shift by minus A, right? X minus A to the power of n. And similarly, if you have your Z's, if that's, we'll call our Z a grid. So we'll end up calling Z a grid. So if our grid is an arithmetic progression, okay, then you have this shift that is here. So that's pretty much this, kind of simple examples you can see. For the falling factorial case, you can see that something similar happens. Okay, and there's a reason why that's true. So some kind of structure more behind this, but I just wanted to point out some examples of what this looks like, when you actually try to compute.
One question?
Yes.
So here, so more or less, you would take your binomial polynomials, and you would evaluate at the z's. That seems to be the pattern here, more or less. Is that?
Yeah, kind of. Yeah. Yes. Yes, you evaluate. So your polynomial is dependent on x, is dependent on delta, and is dependent on the grid. Yes. So, and I'll give an expression later as one of the properties. I think that's the next slide, where I'll talk about how you can actually get these z's. these Goncarov polynomials, I mean, directly. Okay, so yeah, this is what I wanted to talk about. So let's recap. So I'm given a polynomial of binomial type, that sequence, and there's a delta operator that is uniquely connected to that sequence. Now, if you add a grid Z to that delta operator, then that completely determines for me the Goncarov polynomials, okay? Now, so far, what I've said is that if you go back here, I said for you to go from here to your delta operator, remember you have to go through the generating function, the compositional inverse, and then you get the delta operator. And then from the delta operator, in the next one, you can then get, you know, your Goncarov polynomial. So that's like a whole process. Now, one of the properties, and this was by Lawrence, Tringali, and Yan, is that you can actually have a linear recurrence that kind of gives you an alternate route, so that now you can go directly from the polynomial of binomial type to your Goncarov polynomial. So your Goncarov polynomials can actually be gotten by this linear recursion here. Another property is shift invariance. So you can shift things. So there are two types here. But the key thing I wanted to say here is that really what it comes down to is that what really matters are the constant terms, okay, because of this shift invariance. So we can just focus, in a sense, on the constant terms, because that kind of gives us all the information we need. Okay, so let's go ahead and talk about classical parking functions. So back to combinatorics, you know, just regular enumerative combinatorics, we know parking functions are sequences, right? So let me kind of explain where this comes from. So parking functions are these nice objects that were studied first from computer science, okay, where you're talking about hashing functions or in computer storage. So you have a set of files you want to store in a linear order, and you have to kind of go in that order. So another way to look at it is actually in terms of parking, right? Parking cars on a one-way street. So you have n cars that want to park on a one-way street with n spots. And each car has a preference. Car 1 has preference A1, car 2 has preference A2, and so on, and car n has preference A sub n. And each car wants to park in their preferred spot. However, when they enter the street, again, remember it's a one-way street, if their preferred spot is open, they park. Otherwise, they have to move forward and park at the first available open spot. Now, if all the cars can park based on that preference sequence, we say that is a parking function. Otherwise, we say parking fails, and so it's not a parking function. So here I have, I mean, another equivalent way of saying this is that if you rearrange the sequence in, you know, non-decreasing order, then what happens is that your ith term is going to be less or equal to I. And if you think about it, it makes sense because you want enough cars preferring earlier on in the street so that they can park. Because the more cars want to park at the later part of the street, the more the likelihood they will not be able to park, or at least one of them might not be able to park. So let's look at an example here. I think I should try to, let me try to draw on the screen. Okay, so let's try to see how this example works. So 2412. So you have a car, a street with 4 spots, spot 1, spot 2, spot 3, and spot 4. And then you have car 1 has preference 2, car 2 has preference 4, car 3, and this is car 4. So the first car, so let's assume they're going from left to right, okay, this direction. So the first car enters the street and has preference 2. So 2 is open, so car 1 parks. The second car has preference 4. It's open, so it goes there and it parks. The third car has preference 1, which is open, so car 3 parks here. And lastly, car 4 wants preference 2, but car 1 is already occupying that spot, so it has to drive forward and park in the first available open spot, which is 3. And so we've seen that 2, 4, 1, 2 is an example of a parking function of length 4. On the other hand, let's try to park using the preference 1, 3, 4, 3. Okay, so we have 1, 3, 4. Oh, sorry, that should be 1, 2, 3, 4. And so you have your first car, second car, third car, and fourth car. Okay, so car 1 parks here, that's fine. Car 2 parks on the third spot. Car 3 parks in spot 4. And car 4 wants to park on spot 3. It's not available, right? And it has to drive forward. So the fourth spot is also not available. So car 4 is unable to park because it has to leave the street. And so we can see that 1, 3, 4, 3 is not a parking function. Okay. So I hope that is clear. Okay, so I want to clear my all drawings so that I can move forward. Okay, so let's try to move here. Okay, so there are several generalizations of parking functions, really. I mean, there's a whole lot of them. And parking functions are like in the center of combinatorics in a sense because, you know, they show up in a lot of places, right? And they're connected to a lot of things. But one very important one that kind of shows up in our work later, which I want to introduce, is this vector parking function. So vector parking functions are, you can visualize them as you're still trying to park on a street, but this time around, it's a longer street, okay? And each car has a preference. But now, instead of saying that whenever you have the non-decreasing rearrangement of a sequence, we will call that the order statistics. So the ith order statistic is the ith term in the non-decreasing rearrangement. So the ith order statistic is bounded above by some term u sub I. Okay, so you're given this vector u, which is non-decreasing, and then what happens is that instead of what we had before, where we had your order statistic bounded by I, now you replace I with u sub I. So this is a generalization. Okay, so these sometimes people call this U parking functions. Okay, and so I mean, whenever you replace back your u sub I with I, we get back our classical case. But for the second example here says if you make your vector u equals 2, 5, then you get these 16 terms, and you can check that all of them these are the only U parking functions you get. Okay, so what this means is you can think of this as a street with 5 spots, and the first car, or the car with the smallest preference, has to have preferred the spots before 2, on or before 2, so 1 or 2. And then the second car has to have preferred the spot on or before 5. So that's really what we have here. Okay, so one more thing, and then I'll move to the next section. Lattice paths. So lattice paths are paths in the grid Z2 that have east steps and north steps. And the one I'm particularly concerned about for this talk are lattice paths with strict right boundary. So the best way to probably do this is to see this example. So if you look at this example, your strict right boundary happens where you have the blue dots. Okay, so the blue dots say that you have a path with east and north steps, but they can come close enough, but they cannot touch the blue dots. So that's why it's called the strict right boundary. Okay, so for example, this is a lattice path 2, 3, 3, 7, because the first step is at 2, the next 2 steps are at 3, and the last step is at 7. And the blue dots happen to be at 3, 4, 5, and 8. So that's just an example of what a lattice path with strict right boundary is. Okay, so let's talk about the problem that we set out to solve for this particular project. So remember, we have a polynomial of binomial type. That's that basic polynomial connected to this delta operator. You add a grid to the delta operator, and you get this Goncarov polynomial. Now, our objective, or our main question here is, can we find the combinatorial interpretation for any sequence of generalized Goncarov polynomials? And the question may be, what's the motivation for that? Like, how are we able to recognize that there's some, there's probably some combinatorial interpretation here? So a few of these are just some of the results that people have gotten. So in 2003, Kung and Yan had this result that says, if, in this first case I talked about, just the case where your delta is your differential operator, then this is exactly the constant term you get for the Goncarov polynomials is exactly the number of U-parking functions. Then in 2006, Kongson and Yan showed that for the following factorial case, your Goncarov polynomials is n factorial times this lattice part with strict right boundary. So we can see these two examples of combinatorial interpretation, but these are just two cases of delta. So in their 2018 paper, the Lawrence, Stringali, and Yan paper showed that there's a class of structures called reluctant functions. So these reluctant functions were first introduced by Mullin and Rota, but they showed that in this case, so whenever you have a rooted tree-like structure, then your Goncarov polynomials is the number of these reluctant functions whose final images are U-parking functions. So I won't go into details about much of what reluctant functions are, but when you kind of draw them out, they can give you the picture of a rooted tree structure. Okay, so what does this say? Well, we've been able to get interpretations, combinatorial interpretations for these two cases, and specifically a class of cases, but this is not general enough. Okay, the question is, what in the arbitrary case, what happens? Okay, so let me talk about our initial attempt to be able to solve this problem. So what we did is to use this concept of exponential families. So I think it's in Stanley's book. It's also in Will's book, this generating functionology text, where he talks about exponential families in terms of cards, decks, and hands. So think about playing cards, right? Cards, and then a deck is a collection of cards of the same kind of suit, I believe. And then a hand is you pull cards from different decks. So think about it that way. In the same way, you can think about exponential families. So for example, let me say, for example, two regular graphs. Okay, that's an exponential family. Two regular graphs. And a card will be a two regular graph on, which is really a cycle, on n vertices. Okay, and a deck will be all collections of two regular graphs on, well, there's only, I mean, how many? So but the key thing is that each deck contains all the different types of such cards on n vertices. And then hands will be, you can pull out multiple from the same deck, or maybe one. But the point is, you have a collection of cards from different decks. And so d sub n, dt here is the deck enumerator. And hn of x, we'll call this the hand enumerator. So the hands are the number of hands of weight n that consist of k cards. Okay, weight in the sense that when you sum up the number of vertices on all of the cards, you get n. Okay, so the whole concept here is that the hand enumerator is actually a polynomial of binomial type for any exponential family, because it satisfies this expression. So this expression connects the hand enumerator to the deck enumerator for any exponential family. And so, I mean, another way to actually think about this hand enumerator is that you're saying you want to, if you're given a set x, and in other words, 1, 2, 3, up until small x, okay, we want to think of this as the number of card labelings. Okay, you're labeling each card where every card gets the same color or the same label. Okay, and you're of course summing up over all hands, okay, that you could possibly pick. And so that's really what you have here. So what we showed is that the Goncarov polynomials in this case is the number of labeled hands of weight n whose label sequences are U-packing functions. So again, it shows that we actually have some combinatorial interpretation here. And actually, exponential families are a generalization, right, for the third case I talked about here, because rooted tree-like structures are examples of exponential families.
I'm sorry to interrupt. Is there like a place nearby that we can take a 5-minute break just to continue the talk? Is there a good place to?
Yes. Once I'm done with it, I think I can.
Thank you.
Yeah, sure, no problem. Okay, so I would, okay, yes, I think I have, yes, so I'll stop on this slide. So an arbitrary, just in general, like I said, exponential families generalize reluctant functions, and all of what I've talked about are special cases. So the question is, in general, what happens? And so the first question is there a way to find a universal representation that gives us binomial type polynomials? Okay, so that then we can then talk about the generalized Goncarov polynomial coming out, as a result of that. And the answer to that first question is yes, by Nigel-Ray in 1988. And I'll talk about that when we come back. But the point so far is that we want to find a combinatorial interpretation for Goncarov polynomials. But at this point, we want to first say, is there some general way to represent binomial type polynomials that will give us any arbitrary binomial type polynomial, which means you get arbitrary delta operators, and then you can talk about arbitrary Goncarov polynomials. Okay, so I'll pause here, and then when we get back, I'll continue.
Let's continue, Ayo, all yours.
Okay, thank you. So just a quick recap of what I've said. Remember, we're given we're given a polynomial of binomial type. There's a delta operator connected to it. If you add on a grid, then you can completely determine the Goncarov polynomials. So the objective is to be able to find a complete combinatorial interpretation for any sequence of generalized Goncarov polynomials. And I said the first question to ask is, first, can we find a universal representation for binomial type polynomials, which can then lead to what we want? And the answer to that is yes, by a paper by Nigel-Ray from 1988. Okay, so this takes us to partitions. And I guess some people here are familiar with this. So, well, when you get to partition land, partitions, for set partitions, you have a list. Usually we'll use pi to denote partition, and it's a list of blocks, right? That when each of the blocks are mutually disjoint, and when you take the union, you get S. And your partitions are ordered by refinement, okay? So pi of E is going to be the poset of all partitions of E. So it's there's a partial order, okay? And it turns out the poset of partitions is not just a poset, it's actually a lattice where there's a 0 and a 1. Your 0 is where you have all the terms in, singleton blocks. And the 1 is where all the terms are in one big block. So we'll call pi sub n, that's the lattice we're interested in. Okay, so one more thing before I talk about the example here. So you can form up, if you have pi preceding sigma, we can say that there's something called the induced partition, sigma, mod pi. So where you're considering sigma as a partition in the set pi. So you consider pi as a set and consider sigma as a partition of that new set. So and the class of pi sigma, so this what's it called? If pi precedes sigma, we can talk about this as the the interval, okay, from sigma to pi, which really talks about all all partitions that lie in between, okay, between pi and sigma. So the class of this interval is the sequence lambda, where, you know, lambda 1 says how many blocks, or lambda I says how many blocks of size I do you have, okay, in the induced partition, really. So for example, if you consider the set 1, 2, 3 up until 8, and consider pi and sigma given this way, then you can look at the induced partition here of sigma mod pi. So if you look in sigma here, you have 1, 3, 4, 5 in one block. But in pi, you have them in two blocks. So in the induced partition, you have 1 as one element and 3, 4, 5 as another element. 2 is in a partition by itself, and the same thing with sigma. So 2 is, you know, it's in a block by itself. And then when you look at 6, 7, and 8, in pi, 6, 7 is in one class by itself and 8 is in another. And so when you put that together in the induced partition, 6, 7 is one element, 8 is another element in, you know, in the induced partition. So what happens is that the class of this interval is given by lambda, which is 1, 2, 0, 0, 0, which means that there is only one term here, only one block of size 1. And there are two blocks of size 2, that is 1, 3, 4, 5, and 6, 7, 8.
Mhm.
And then there's no block of size 3, and there's no block of size 4, and so on. So that's what we have. That's just an example here to see how this works. Okay, so let me go ahead and talk a little bit more about weighted enumeration. So I talked already about the interval x to y for if you're given any partition, any poset P, you can consider, you know, if x precedes y, you can look at all the terms that are in there, okay, in between. And so the incidence algebra is just the A algebra of all functions from this interval set of P to A. So throughout the rest of the talk, whenever you see this A, we're thinking about, you know, a commutative ring with unity. So we can define this weight function. Just think about a weight function, okay? W1 to the lambda 1, W2 to lambda 2, where your lambdas are coming from the class, okay, of pi sigma, just like we discussed in that example. So this kind of, it's an interesting thing. And I mean, we'll see an example of how to compute this for, you know, in the case where you're looking at the pi 3, okay, the partition lattice of the order 3. Okay, so this enumerator I want to talk about next, the zeta type enumerator, is what we're looking for. This is what this is kind of what we want here, and this comes from Nigel Ray's paper. So A sub n is essentially saying you want to count the block labelings of the partition pi, okay, using x. Again, capital X is the set 1, 2 up until x. You're using that set to label each block. And remember, each block, when you color any block, each block has, every term in each block has the same color. Okay, so you're labeling all blocks and enumerating this by width, okay? And you're summing up all of this over all the partitions in the lattice, in partition lattice. So it turns out this is what we actually need, right, to be able to get to what we want. But let me show this example first. So for this example, you can see that this is pi 3, right? So really what you want is to say, how do you label all of the edges here? And what you just look at is, for example, this is your 0 term here. This is your 1 element here. Okay, the 0 term, between this and any of the terms in the middle here, you can see that, for example, 1, 2 is in the same block in this at the second level. So 1, 2 are in different blocks in 0. So it means that in the induced partition, I have one block of, you know, with 3 in it, so of size 1, and then I have a block with two terms in it, 1 and 2. So what that means is that when I compute W, the weight function, I have W1 to the power of 1, W2 to the power of 1, and all other powers are 0. So that's why, and of course, I should have mentioned that we're setting W1 to be 1 because we want our polynomials to be monic. So that's what happens here. So eventually you realize that you get W2, W2, and so on. And then the last one, which is from 0 to 1, is the only one that is W3. And in actual fact, the weight, when you take the weight between 0 and 1, it's always going to give you Wn. Because think about it, you're putting together all these singletons into one big block of size n. So only lambda n is equal to 1 and all other lambdas are 0. So that's why we have this. So if you computed the zeta type polynomial, this is what you will get. X, the first one, the next one is x squared plus w2x. The next one is x cubed plus 3 w2x squared plus w3x. Okay, so you can kind of compute that from this. And this, it turns out, gives us the framework we actually need. Okay, so the important result by Ray is that, this that we just computed is actually a polynomial of binomial type. So this polynomial set. And you can see that with the weight function, this becomes arbitrary because your weight can be anything you want it to be, really. So this is arbitrary, and lambda, if lambda is the delta operator whose indicator is given by wi times t sub t to the power of I over I factorial, then it turns out that your a sub n is the conjugate sequence. So in other words, we've been able to find the power series that corresponds to, that is the conjugate sequence for your polynomials of binomial type. So essentially what we're saying is that by Ray's result, we have that framework that we need of an arbitrary polynomial of binomial type. And now we can work on this to get an arbitrary, the arbitrary Goncarov polynomials. Okay, so let's come to talk about Goncarov polynomials in this context of the partition lattice. So what we do, remember from some slides before, I talked about that recurrence relation or that linear relation that takes you from your basic polynomials to your Goncarov polynomials directly. So that's really what we are using to define 4 here in the context of the partition lattices. And it turns out that this is exactly the end, the Goncarov polynomials from the interpolation equation. So because our AN sequence is generic, our TN sequence is also generic. And now we can try to see, what that means combinatorial. So, okay, before I move on, I should define this. This PF pi of Z just says you're looking at all block labelings such that your labeling is a Z parking function. In other words, whatever labeling you use is constrained by the term Z naught, Z1 up until Zn minus. And so that leads to our main result. So this is the main result. I'll put it up there for like a few seconds and then I'll talk about it. So what we're saying here essentially is that we can find a combinatorial interpretation given any weight function, okay, and a grid. It turns out that the generic interpretation we want is that instead of A sub n, so replace that block labeling with the block labelings that are Z parking functions. So it turns out that your generalized Goncarov polynomial is actually counting all block labelings of your partition lattice that are enumerated by weight. So that's really what is going on. So this is for every possible Goncarov polynomial you can come up with. You can, always go back and see that this actually comes from, like this is the most general form that you will get. So let me just kind of give a sketch of the proof, and then I'll give an example of what this looks like. So what you do is you kind of define this set of these ordered pairs for your partition lattice, and then the block labeling. So for each partition lattice, you have a block labeling, right? And remember that for each block, you label with the same value. Then this SP is a subset of the first set, but these are the ones that have their other statistics are constrained by Z. And so it turns out you can have this mapping that kind of splits open your pi F into these two different pi's. So pi 1 with the block labeling F1, pi 2 with the block labeling F2. The first one comes from this SP set. So pi 1 is a sub partition, and F1 is a block labeling where your other statistics are constrained, and R2, the other one, pi to F2, is whatever you have left, essentially. So it turns out that what this gives us is that you can then argue that, because there's also some property I didn't talk about earlier, but there's some property of multiplicativity of this weight function. So in other words, W of 0 pi, you can split it open into W of 0 pi 1 times W of 0 pi 2. So it turns out that if you kind of do the math here, you get this expression times this, okay, where this is just summing up all your terms from the, SP set. And so that kind of gives you this. So it turns out that we get back an expression similar to equation 4 here, which tells us that since they satisfy the same recurrence relation and have, of course, the same initial terms, then we have exactly gotten our Goncarov polynomials. So this expression here, the sum of the weight times, this count of the set of packing functions, is our Goncarov polynomial. Okay. So what does this look like as an example? So like a small example here would be if you wanted to compute T2, okay, the constant term of the Goncarov polynomial T2 in general, you would have this expression, 2z0 z1 minus z0 squared plus W2 z0. This is the most general form of the Goncarov polynomial. Now, on one hand, computationally, this is what we have, right? But if you wanted to count, so on the other side where you're looking at the combinatorial meaning, it turns out that you're looking, just at the partition pi 2. So for this partition, you just have two things here, right? This is just all block labelings where you're considering the partition 0. And on the other hand, this is all block labelings for the partition 1, where you're multiplying by W of 0, 1. This one is multiplied by W of 0, 0, but that's just 1 by definition. Okay, so what we have here is this cardinality of this set plus W2 times the cardinality of this set. The first one, this is PF1 of Z, is really just you have, so let me try to draw here and see what, so that we can see what's going on. Okay, so remember that you have, in this case, the one element in pi 2 is just the block where you have, 1 and 2 in the same thing, okay, in the same block. And remember, we must always color each block with the same color, okay? So essentially, this is saying, however you rearrange, your terms are bounded by Z0, okay? That's the block labelings here, are bounded by Z0. So there's only Z0 possible ways to be able to do this. Okay, so that's how we get this. And for the second one, we're saying you have two blocks. One, maybe one has one here and the other one has two. And you're trying to label each of these blocks. So we're saying that the labelings here are bounded above by Z0, and the labelings of the second block are bounded above by Z1. It turns out that the picture for this is what is right on the left here. So if you want to label, you have 1, 1, 1, 2, 1, 3, and so on, up until 1 Z0. Then you keep going up until you get to 1, Z1. Okay, and you do the same thing. Just list out all of those terms. And if you look at this, you see that what you have is you have this rectangle here, and you also have this rectangle here. So if you think about this rectangle, how many terms are here? There's Z0 times Z1, okay? For this other rectangle, there's also Z0 times Z1. So if you add that up, you get your 2Z0 Z1. But we've overcounted, right? We've double counted this square, and that's the Z0 square. And so you see that this is exactly what we have. Okay. So I hope this example kind of, at least, throws some light on how this works.
So one question. So I guess even though there's a negative sign on one side, you're counting something, right?
Yes,
the overall
exactly.
Counting something.
Yeah. I mean, and that's the whole point, right? That's why we wanted this whole thing for W, because in general, we were always counting something. So that's why I didn't touch on it earlier, but I was saying something about this certain non-negativity that is required for the previous cases, right? You're counting something. Even in the following factorial case, you're counting some kind of tree structures, But in general, what about, if I wanted W2 to be a fraction, if I wanted my W's to be fractions, whatever I wanted it to be, rational numbers. As long as, W2 can be something, I have a general picture that tells me what this looks like. So, well, the next slide, which is really just saying that all of the known examples are special cases. So remember when I talked about all the three different, examples or classes of things, it turns out when W2 is 0, then this 2Z0 Z1 minus Z0 squared is exactly the number of Z packing functions. When W2 is 1, you get the case for the following factorials. When W2 is D2, you get the case for the reluctant functions I talked about. Okay, and so all of these are just special cases of, the general form that we just found. And, we can just say that these are all generalizations of packing functions. So there's some sort of packing function thing going on here throughout, or some kind of generalization. Okay, I think I'm almost out of time, so I'll just end here, the summary. So remember, you saw this picture at the beginning. So now it makes sense. You have basic polynomial, which correspond to your delta operators. Okay, it's a one-to-one correspondence. And then on the other hand, your basic polynomials are counting structures, right? Coming from counting. I mean, I didn't go into the details of all of the structures they count, but you've seen that in general, we're looking at something in the partition lattice, which is really underlying each of the structures you can talk about for all of them. So what we've shown is that, well, prior to now, by Lawrence, Tringali, and Yan's work, we know that there is, a linear transformation that gives you the Goncarov polynomials directly from the basic polynomial. But also, you could have found the delta operator and using interpolation found the Goncarov polynomial. Okay. Now, the last part that was missing was this part. Okay, this was the part that was not closed up. So this was what our work did, to say that the full interpretation for the for Goncarov polynomials is that it's counting these structures in the partition lattice and enumerating this by weight, but it's specifically counting those that are the block labelings that are constrained by their other, or whose other statistics are constrained. In other words, some kind of generalized packing functions that are weighted. So really, this is the summary of what this project was about. And so we kind of closed up what was missing here. Okay, I think I would stop there. Thank you. And I'll take any other questions you might have.
Very nice. Do you have any question?
so I just have a question. So you have these like PF pi's. Can you somehow count those maybe with some kind of Mobius inversion in terms of the Goncarov polynomials, or those are usually easy to count, the PF pi's, the part of these I mean, how, yeah, are those, is that part easy to count in your main theorem? Like,
yeah, oh, I see your point. Yeah, I mean, I think it depends on what you're looking at, right? So, I mean, so from Ray's work, there's definitely some, if you want to think about this, so this polynomial a sub n, there's a Mobius transform for this one. There's a Mobius type, zeta type weight that you can define that kind of gives you, you know, so some kind of Mobius inversion that happens that you can get a polynomial that's kind of the conjugate for the delta operator of this one, if that makes sense. So yes, there's some certain sense in which you can have a different weight, and that Mobius inversion will kind of give you something a bit different from this. Yeah, but yeah, I mean, computing this, when it becomes bigger, maybe not so easy, but it can be done. Yeah, not so easy like directly, but I think you can actually, you know, like do the computation.
Okay, any other question? So we thank Ayo again. Thank you very much for the talk. I really like it.
Thank you.